Yeah. So is my screen visible? Can someone please?
Yes, yes.
Yeah. Fine.
Yes, sir.
Fine. Fine. Thank you. Thank you. So let's start. So this is what? Today I will be covering the content of week 5. Okay. So this is analog IC design. Uh, and my name is what? My name is Mayank Anupam. And I am also a PMRF scholar. For those who are joining for the first time. And this is analog IC design, and it is taken by Professor Shankar Aniruddhan. He is professor from the Department of Electrical Engineering at IIT Madras. And myself, I am Mayank Anupam, and I am at IIT Kanpur, electrical engineer, PhD student. Fine. So let's proceed with this week's content, week 5. Today I'll be covering about the content that was covered in week 5. Okay. So in week 5 we saw what? We saw basically an extension of what was taught in week 4. So in week 4 we saw a two-stage Miller compensated op amp, right? So quickly recap. So in week 4, let's leave it like this. We saw what? Two-stage op amp. We saw two-stage Miller compensated op amp. And how did it look like? So we have this op amp first, and then we have this another op amp. We have another capacitor here, which is providing Miller compensation. We have its output resistance. We have a load capacitance here. We have GO2. This is minus GM2. Okay. We have this capacitor CC, and here we have the first stage output conductance, and this is the first stage parasitic capacitance. This is GO1. Okay, fine. So this was the Miller compensated op amp, right? And in this we saw that we analyzed it, right, in detail, and we saw that its pole P1 was approximately given by what? Can say anyone tell me what was the approximate location of pole P1? The first pole at this node?
GM not by GM01 divided by C into GM2 by GM0 plus 1 plus C1.
Correct. So right, this is a approximate location of pole 1, but you can say for all practical purposes this C1 is much less compared to this other guy, right? So we can ignore this. Okay, and moreover this GM2 by G02 will also be much greater than 1, so we can also ignore this. Okay, so this is approximately the pole location. Okay, it is G01, basically the output conductance of the first stage, divided by the capacitance CC, this is CC, which is multiplied by the gain of the second stage, DC gain of the second stage. Okay, fine. Now can anyone tell me what was the approximate location of pole P2?
It's GM2 by CL.
Correct, it is GM2 by CL, approximately, right? This is under what approximation, by the way?
C is much greater than C1.
CC is much greater than C1, right?
Yes.
This is extremely necessary because otherwise what will happen? Can you tell me?
Sir, we got a quadratic equation to find C. Otherwise, if CC is much greater than C1, then we got a linear equation.
No, no, but that is true. I mean, can you tell me what happens if CC stops becoming much greater than C1? What happens here?
One
Uh,
pole
The
will come
factor
before
also.
yeah, yeah.
one pole will come before unity game.
Okay, so
Two
that
pole will two pole will come before unity game.
yeah, yeah, so all that is fine. So the thing that will that you can understand from right from here itself is that you see how did we find pole P2? We injected a voltage here, right? We put a voltage source here and saw what was the current coming out, right? And what was the current coming out? It this voltage first VT was getting divided, right? Cap division was happening, right? In between this CC and C1, correct? And this was appearing here in the like if we apply Vt here, then the voltage that will appear here will be what? Use another color. It will be what? Vt times Cc divided by Cc plus C1, correct?
Yes, sir.
Right. Now if Cc is not much bigger than C1, what will happen? This voltage Vt here, the voltage that will appear here after division between these two capacitors Cc and C1, okay, it will become very less, okay, and that is something we do not want. Ideally what we wanted is GM2. We What was the purpose of adding this capacitor CC? The purpose of adding this capacitor CC was to make sure that at very high frequencies, okay, this GM2 is connected in a diode connector fashion, okay. So at very high frequencies, this GM2 will simply appear like this at very high frequencies. It will be like this. It will simply be shorted, isn't it? At very high frequencies. Because this capacitor will be effectively short, right? At very high frequencies. So this GM2 will appear like a diode connection. You remember this, right? This is a typical diode connected GM2. This is a diode connected transconductor. And the usefulness of this diode connected transconductor is what? It provides very low impedance. So am I making sense? Everyone is following me? What I'm saying?
Yes, sir. Yes, sir.
Yeah. So that was the whole purpose. So CC has to be much larger compared to C1 to make sure that this GM2 maintain its usefulness. Okay. If CC becomes comparable or even lesser than C1, basically this Miller compensation will not be happening after that. Okay, so everyone was correct. So everyone was saying me that this poles will come closer and all. So all that is fine. So I just wanted to give you a sense of what happens if CC starts becoming lesser. So what actually happens? So this pole actually starts to come closer, but that happens because your this gap division here at between CC and C1 is not happening properly. That is why. Fine, fine. So let's move on. Let's remove this. Fine. Okay, so now we also know in this week what did we see? We saw that because of this CC and this GM2 here, what happens? We also have a zero, right? We also have a zero in the circuit. And what is the approximate location of zero? Oh no, what is the exact location of zero?
GM2 by C.
Correct. GM2 by CC, right? Fine. And now tell me, can someone tell me what was the means how did zero come here? I mean, what is the intuition behind this zero? Why should a zero appear?
In the second stage, there are two paths for the output.
Correct. And which are those two paths? One is this one, right? Sorry, let me use another color.
One through
One is this one.
transconductor channel to
One is this one,
through
right?
CC.
Yeah. Can you speak up once again?
One is through GM, the
Correct.
transconductors, and another
Correct.
through CC.
Correct. Definitely, yes. So these are the two paths because of which we can expect a zero. So did everyone understand what means? Why do we say that if there are two paths with different phase shifts, then we can expect a zero in zero in this circuit? Did everyone understand that?
Sir, can you repeat?
Yeah. So in the lectures, We saw that, right? Because this circuit has two paths, isn't it? This output, from input to output, we have two paths. Do you identify
Yes,
the
sir.
two paths?
Yes, sir.
So which are the two paths?
The op amps.
Yeah, so where is the input, by the way? This is the input, okay? And this is the output. And in between this input and output, there are two paths. Can you tell me which are the two paths?
One from CC and the
One
other one
from
from here.
this guy here, from like this, right? And which is the other path? Yeah, which is the other path?
Through both the GM stages.
Correct. So the student which asked me earlier,
Yes, sir.
can you also identify that this is the second path, right? Direct path like this. This is the second path.
Yeah, the straight path.
Correct. Now these two paths, they will definitely have different phase shifts, isn't it? I mean, what do you
Yes, sir.
understand by a zero? So if there is a zero like this, 1 plus s by z divided by 1 plus s over p1 plus into 1 plus s over p2, if there is a transfer function like this, then this is a zero, right? S over z. And what happens when you hit a zero? So h of z, h can also be written as v out over v in, correct? So when
Yes,
there is zero at zero frequency, what will happen? This guy will become zero, right? So V out will become zero irrespective of input voltage, correct? So at the
yes,
zero
sir.
frequency, irrespective of what input you apply, you always get a zero at the output. Zero means you will get a null voltage. Nothing will be. I mean, it will be nothing will happen. No output will not be. Output will be zero even if you apply any input at that frequency, at the zero frequency, right? So that is why this is zero. Okay. So here also you see that. One second. So let me put it here. Yeah. So here also you see what is happening. We have these two paths, right? One through CC and other through GM2. Okay. Now these two paths, they have different phase shifts, isn't it? So first of all, from input, which is here, we have same path up till here, right? Up till this, everything is same for both the paths, right? But right from here, we have these two branches which are bifurcating from here, right? And then they are again combining at the output. Okay. So any signal, any current that will pass through this CC and which will be going through this GM2, they will have different phase shifts. Did you understand this?
Yes,
Why should they have different phase shifts?
yes,
The
yes.
current which is passing through these two, they will have different phase shifts, simply because if you apply a voltage VE here, let's say there is a voltage VE at this point, then what is the current which is going to pass through CC?
Uh,
VA minus V naught
DC.
into SCC.
Correct. And what is the current that will pass through this GM2?
That will be into SCC, right?
Oh,
Current.
sorry, right, my bad. Correct. And what will be the current due to GM2?
GM to
Minus.
B.
GM2 times VE, correct? So you see that one is a current directly due to a transconductor, and another is a current which is due to a voltage across a capacitor, right? So definitely these will have different phase shifts. They will not be same kind of, right? Current passing through two resistors, they have the same behavior. Current passing through two capacitors, they have the same behavior. Current passing through two inductors have the same behavior. But a current passing through a resistor and a current passing through a capacitor, they do not have same behavior. Did you understand that? So this same behavior concept is also, I mean this same behavior thing is loosely translated for what? Phase shifts. So current passing through a transconductor and current which is passing through a capacitor will have different phase shifts. Okay. And when these two phase shifts current add, they can potentially become they can add to become zero, right? I mean what will happen here is that at the zero frequency is that Uh, so let me mix. Okay, so what will happen at zero frequency is that basically at zero what will happen, this current which is coming from here, okay, and this current which is coming from gm2, this will be of opposite signs, okay. This current which comes from cc right here will directly go inside gm2. It will not be going anywhere into cl or g02. Did you understand that? At zero frequencies, at zero frequency, all the current that comes from cc will directly go inside gm2 and will not be therefore will not generate any voltage. So that is why we get a zero. Is that understood now?
Yes, sir.
Right. So
Yeah. Tell me.
about the part when you said that the current is opposite to each other, can you just explain that part? When I do understand that the current is leaving the transmit the op amp and entering the capacitor, so it is opposite in sign. But that part when they cancel each other out when at zero frequency. Can you just explain that part again?
Yeah, definitely. So leave these things, right? So up till here everything is same for both these paths, right? Before this everything is same for both these paths. Now any current that will be passing through this at zero frequencies, you know that the voltage at this point will be zero, correct?
Yeah.
Yeah. Now voltage at this part is zero, and and how should that become zero? If the voltage is zero here, no current can go inside, right? Current flowing through these two guys will be zero, correct?
Okay.
I mean, there is no ambiguity in that, right? Right. If the voltage is zero across any element, current passing through that should be zero. I mean,
Yeah.
okay. So it's a linear element, so voltage is zero, current is also zero, right?
Yeah.
Now,
Ohm's law.
correct. Fine. So after, so what I'm saying is, any current that will come from here, okay, from here, cannot go here. Everything will be absorbed by this only, absorbed by this conductor only. That is what I'm saying. At the zero frequency, at the point where zero happens, at the frequency which zero happens, at that frequency, all the current that this capacitor is carrying, cc is carrying, will simply be absorbed by this transconductor gm2. Okay.
Okay. Which is the same as saying that the output is going to be 0 volt.
Correct.
Yeah.
Definitely, yes. I mean, that is how output will be zero. Otherwise, how will the output be zero? If there is some current which is leaving, then there will not be then output cannot be zero, right? Current has to be zero. The current flowing inside these two has to be zero, right? Only then we can say that the output is zero. There is no other way,
Okay.
right? So from this we can quickly calculate, right, what is the zero location. I mean, let's say the voltage here is VE, and the voltage here we know that at zero it has to be zero, right? V0 has to be zero, correct? So the current that will be going through this, what is the current that will be going through this? Through the capacitor CC? No, what is the current which is going through this capacitor CC? This
Same as
voltage is,
GM
no,
same
no,
as with this. Yeah.
GM2 is CC
no, no.
into VE.
One
See,
second.
1 by SCC into VE.
Correct. SCC into V, right? The current that is passing through the this thing. So current so at zero frequency. So let's remove this. At zero frequency, what will happen? The current through CC is equal to what? VE times SCC, correct? And current through GM2, what is that? I mean, current at the output of GM2, what will that be?
GM2 VE.
GM2 VE. And what is the sign of GM2 VE, by the way?
It is minus sign. If it is going outward, it will be
No,
minus, and
this
if it
what
is
you see. This is minus sign at the input,
yeah,
right?
then it is minus.
Then it is going inside, right? The sign of this current through GM2. It should, okay. So we can also apply V minus sign here also, right? Fine. And from here we see that these two currents will be equal at the point where 0 happens, right? These two currents have to be equal. So at 0 frequency, VE times SCC has to be equal to what? GM2 times VE, isn't it?
Yes.
Correct? So that is why we get the location of 0 like this also. So from here we can find out S is equal to what? GM2 by CC, right? This is the location of 0. We got so some one of you told me earlier also, this is GM2 by CC. So we can also visualize this like visualize the location of 0 in this manner, that the two currents, they are basically the current this current here is completely encircling inside this trans conductor. Okay, so that is how you can visualize this. Is that fine?
Yes, sir. Sir, can I ask you a question from previous assignment about there also we have to find zero frequency.
Yeah, tell me.
There I used the formula GM2 by CC. I got correct CC in the answer, but I got wrong zero.
So I mean if you have done no calculation mistake, then it makes no sense. This is
So
a zero frequency.
in assignment two question is there is also zero is equal to GM2 by CC. No,
Yeah, 0 is GM2 by CC only. Yes.
there
Actually, I think you forgot to convert rate
I
to
have converted
hertz.
in megahertz.
No,
So
GM2 by CC is in radian. You have to convert by dividing 2 pi. Then you got hertz.
That's
so
so that,
so and
but they ask in
did
megahertz.
anyone, no, 1 second, did anyone else get correct answer for that?
Yes, sir, I got.
Yeah, so maybe you can tell him. So basically answers are correct. Okay, so if you
Sir,
have done no
GM by
calculation
CC is
mistake.
correct, but you have to divide 2 pi to get in hertz.
Yeah, right. So basically if you have done no calculation mistake, then you should not
Okay.
be wrong. But by the way, the
Okay.
thing is that your answer, your procedure is correct. It is GM2 by CC, but yes, this is again radian per second.
The same goes with omega u.
Omega u also is in radian per second. Yes.
Okay. That's why maybe I got wrong answer.
Yeah. So Venkat, yeah. So you have raised your hand. You have a doubt?
Yes, sir. Yes, sir.
Yes.
Sir, as per the lecture, so when I use the quadratic equation to solve this value for C, I got around 925 femtofarads, sir.
Okay.
That is beyond the given range.
Maybe you have done a calculation mistake.
No, see, I calculated twice, sir, this by using quadratic equation.
Using quadratic equation is coming at around 690 at around
Can you please make a calculation for that CC so that everything will be clear of that as well?
Okay, sir, I will check it. Sir, please tell me the value again if I use the quadratic equation method.
So what you can do is that I mean these questions you can discuss later. I mean, okay. So definitely
Okay,
if you
okay,
have
sir.
a problem, that means you have made a calculation mistake. If there is no conceptual mistake, then you have made some calculation mistake. Okay. So so you should basically check your calculations a lot of times before submitting it. Okay. Then you
Okay,
No,
may.
okay.
sir. Actually, if we consider the quadratic equation,
Mhm.
then we got above 99,000 femtofarad.
Sir, there is one
And if you
category.
consider the linear equation for
Mhm.
calculating C,
Mhm.
then we got the range that given in the
So what was the
assignment.
question, by the way? Let's see. Week
Find
four,
the value
right?
of C.
Week 4, right?
Yes, sir.
see. Uh,
Hello, sir.
yeah.
Sir,
Yes.
I think they missed the RL, sir. RL is also present, no, sir. That
Yeah.
GO2 equals to
Correct.
G. Yeah.
Yeah, yeah. So if someone is getting correct answer, that means something is wrong with your calculation, right? Something is wrong. So
Sir,
I
I
have not.
got the correct answer by using GM2 GO2 plus GL divided by C1 plus C2 plus CL.
Okay, so
I got it right.
okay, so fine. So if you are using everything, if you are getting a correct answer, means you are fine. I mean, I have not personally solved the questions myself. Okay, so if you have, if you are saying something is wrong, I'll have to do it myself again. But the thing is that all the questions that I'm doing in this tutorials, it is more or less the same kind. So the point is to understand what is the procedure and what are the concepts. Okay, and if nothing is wrong, calculation should be fine. Then you should get the correct answer. Anyway, so that
Sir, I have a question related to week 5, sir.
yeah, go on.
Yes, just
Sir,
like in the last lecture,
Yeah,
sir told that if you add a register divider
yeah,
to for the k gain,
huh,
then the position of poles and zero are not changed, but the omega u loop is changed. Okay, come closer to the py.
yeah, correct.
Yes, and
Yes.
the phase are also not changed.
What
Okay,
what what will not change?
F- sir, phase plot.
No, no, phase plot. Why will it not? Yeah,
The
phase
phase
plot will
plot
not change. Yes.
not change. The
Yeah,
phase
phase
margin will
plot will not.
change.
Yeah, phase margin will change.
Will
Yes.
change.
Yes.
Yes.
Yes. Yes.
So then, how to get the omega u loop, sir? The new omega u loop when we consider the k gain.
No, no, the omega u loop will be simply omega u over k, right? I mean, uh, let's say this was your loop gain earlier. This you have pole P1, then you have pole P2 here. Okay. Now if you decrease, if you increase k, that means your loop gain will decrease. Okay. So let's say your loop gain comes down like this. Okay. So your new location of omega u will be this one, but
Yes, sir.
P2 will not change, right?
Yes, pole and zero location are not changed.
Not
Yes.
change. So you can see this omega u has changed. So you can get this omega u in the basically your loop gain will have have like this, a term like this, 1 over k term like this, right? Use that to get omega u loop.
Okay, sir.
Yeah. So
Sir, one more question from
yeah,
closed loop bandwidth. I'm not getting that point.
I mean, what are you not getting?
Closed loop bandwidth. But this is similar to the
Yeah. So closed loop
means
bandwidth. I mean, did you not understand what is a closed loop bandwidth?
yes. How this is asking the cutoff frequency.
Yeah. So closed loop bandwidth is nothing but the uh, 3 dB bandwidth minus 3 dB bandwidth of closed loop system. And so do you understand what is a closed loop system? This is a closed loop system if you have this condition like this. So this is a closed loop system. This whole thing is a closed loop system, and if so the 3 dB bandwidth of this closed loop system will be the closed loop bandwidth. Okay, and this is an open loop system. If we break this loop here, then in that case, and if we apply an input here, and let's observe the loop gain, then that loop gain is also called this. Basically, that loop gain will have a UGB which will be equal to this minus 3 dB bandwidth. Okay, so this is what happens. So this 3 dB minus 3 dB bandwidth of the closed loop system is also equal to the UGB of the loop gain. Fine.
अभी भदोही आने वाला होगा शायद.
What?
Then closed loop and open loop bandwidth are same, sir.
So a lot of guys are speaking at the same time, please. to speak one at a time.
It means open loop gain and closed loop gain are same.
No, no. Open loop gain and closed loop gain are not same. Open loop gain is this one, loop gain, and closed loop gain is other thing. Closed loop gain is between V into V out like this. Okay, but open loop is when you break the loop here. Okay, you short this input, and then you calculate what is the loop gain. That is your open loop gain.
How you calculate closed loop gain? Can you tell me again?
Yeah, so you do this. You apply an input here. You basically the system that is given to you. In that system, you find the gain between input to output. Let's say this is the input and this is the output. Okay,
Yes.
and this is the whole system, the actual system. This is the actual system.
Yes.
So in this system, you have to find the gain between this V into V out. So that is the closed loop gain. Fine. So let me move forward now. So otherwise, you have difficulties covering. Fine. So what was I saying? Yeah. So this is a zero frequency, right? So after that, how do we cancel this zero? By the way, how do we cancel this zero? I mean, this zero is dangerous, right?
This is
Inserting
If we,
register.
if we make the GM much larger, then the zero goes beyond omega u loop. Then we got a first order system between P1 to omega u loop.
One second,
So
one
there
second.
is no effect of zero.
Yeah, go on. Can you speak once again? I mean, there was a lot of
Sir,
noise here.
when we make the GM much larger,
Uh-huh.
then the position of zero is beyond the omega u loop.
Right, definitely. I
So
mean, that is also
we
one way.
can avoid the zero effect.
Correct. I mean, this zero location is GM2 by CC, right? So this
Yes.
zero is why is this zero bothering us? I mean, why do we want to cancel this zero? Why is this zero dangerous? I mean, why is it not desirable? What is the problem if you have this zero in the circuit?
It is situated in right half plane.
Correct. So this zero here is a RHP is an RHP zero, right? This is an RHP zero, and this zero, any zero in the right half plane, will add excess phase delay, right? It will add delay. It will simply add delay to the closed loop system. Delay to the negative feedback, basically. And we remember, right, that delay in the negative feedback is absolutely no, correct? So delay can cause instability in the negative feedback system. So that is why this RHP0 is not desirable, because it introduces extra delay. Right half plane 0 is not desired because it adds extra delay to the negative feedback. So that is why we want to cancel this 0. How do we cancel this 0? So one way that one of you told me is that simply increase the GM2. That is true. If you increase the GM2, if you make GM2 very large, and this goes beyond omega u loop and much beyond omega u loop and P2, basically then you do not have any problem. Fine. But a lot of times that is not desirable, simply because this GM2, it will be implemented by using some transistors. Okay, if you want to increase GM2, you will have to increase the size of those transistors. Fine. And the size of those
So the
transistors,
power
consumption will simply go up.
Yes, yes, I
Fine.
understand.
So that is why it is not desirable. So other thing that we can do is what? We can simply add a resistor here.
Yes.
Correct. This resistor, its value should be what? Again, we can do the same thing, right? We can calculate the same in the same way. What should be the value of RZ? Let's say we added a 0. We added a resistor RZ, and we do not know what should be the value of this resistor RZ. How do we find out? We do it in the same manner. We find out by calculating what is the 0 location. Okay. So how did I calculate 0 before RZ was there? I simply assumed that V0 is equal to 0 at the 0 frequency, right? And after that, what we can do is we can simply write here the same equation, right? The current which is flowing through this will be VE into, and what is the effective conductance of this CC in series with RZ? It will be SCC divided by 1 plus SCC RZ, right? So this is the current which is flowing through this guy here. Now what is the current coming out of this node here? It is gm2 times ve, correct? Hello?
Yes, sir.
Yeah, am I audible to you?
Yes, sir.
Yeah, so I was saying that uh, how do we calculate the required value of rz if we do not know what is the value? I mean, we know that rz is required, okay, but we do not know what is the value of rz. So how do we find it out? We do it in the same manner as we did earlier, okay. So this is, let's say, our uh, yeah. So at the zero frequency, what will happen? Again, now I'm trying to find out what is the value of rc, okay. So at the zero frequency, the current through this capacitor cc and this, they will simply circle inside, right? No current will go inside here, and this v out will be equal to 0, correct? So what I will do is, I will again use the same formula, which is the current passing through this guy here, which is v times scc divided by 1 plus scc rc, and that has to be equal to the current coming out, which is equal to gm2 times ve, right? Everyone is clear on that?
Yes, sir.
Fine.
Yes,
From
sir.
here,
The conductance is SCC by SCC plus RZ, right? 1 plus SCC.
conductance is fine. It is scc by 1 plus, it is the admittance, net admittance, right?
Impedance, okay.
This is admittance. You see, cc and rz are in series,
Got
right?
it, sir.
Fine.
Got
Yeah,
it,
yeah,
got
yeah,
it.
fine. So basically, after this, we can simply calculate the zero location, right? Again, so this will be what? scc is equal to gm2 times. Uh, so this is cross multiplication here. So gm2 times gm2, sorry, s cc rz times gm2. Fine. So from here, what is the zero location? S cc minus cc rz gm2 is equal to gm2. Fine. So what is S is equal to gm2 upon cc minus cc rz gm2. Fine. So now can you tell me what is the required value of gm2 looking at this equation? I mean, if we add a resistor here, then this is the location of 0, okay. This is the 0 location. So can you tell me what is the what should be the value of rz to make sure that we do not have a 0 in the system?
1 by GM2.
Yeah, so how did you come with that value?
So we want to eliminate the 0.
Right.
So if I put 1 by GM2 in the place of RZ, then AZ will be infinity.
Correct. So eliminating 0 simply means what? At 0 location is at infinity, correct? So that is why we simply have to make sure that, so rz has to be equal to 1 over gm2. So that will make sure that this guy cancels and we have this sz as at infinity. Fine. So this is the way that we cancel 0, correct? Fine. So this is done. Now let me talk quickly about nested Miller this compensation. So we saw that a simple two-stage Miller compensated op amp so this had what? Limited gain, right? I mean, this had gain, some gain, but let's say we want to increase that gain. So one way is
Sir,
to, yeah,
I have a question that uh, what is difference between high frequency and zero frequency? Because DC frequency can also say that it has a high frequency. DC volt also can be said that it is a high frequency because the step response is also at a high frequency.
Uh, I am not getting
I,
your
I,
question.
I am saying that it high frequency means we have a large frequency at very. Sorry,
No, no, you can
sorry,
speak
sir.
in Hindi if you are more comfortable with that.
Uh, I think I get confused. Wait a minute.
Okay, so
I
if you have
forgot.
a language problem, you can speak in Hindi also. I am
No,
comfortable
no,
with
no.
that.
I confused.
Okay,
Wait a
fine,
minute.
fine. So you frame your question, then you can ask me again. Okay, fine. So I was talking about this two-stage mirror compensator op amp. So here we had limited gain, right? I mean, this there are only two stages. So the DC gain, limited gain by limited gain I mean DC gain. Okay. So at DC we have the gain, which is the multiplication of gains of these two individual op amps, right? So this is some gain. Let's say we want to make the gain even higher. So we use multiple stages, right? We use multiple stages in cascade, right? In cascade to realize larger gain in DC at DC, right? So what was that? I mean, one example is simply like this: you do this, you do this, you do this, and now if you have three stages like this, the you understand that why do we require compensation here? I mean, why did we require compensation in two stages also? What was the reason that we added this capacitor? Can anyone tell me? What was the
Pole splitting.
correct? Pole splitting was the main reason, right? I mean, and what was the reason for splitting the poles?
Phase
To
margin.
maintain minus 20 dB at a unity gain.
Correct.
To
Minus
make
20 dB
system
per decade.
stable.
This slope has to be maintained near UGB. And why is that required?
Stability for stability. We will have a
Yeah.
proper
Phase,
response.
Correct. So
total
basically,
phase
if you do
margin.
not add this capacitor here, what will happen? Then we have from input to the output here. Okay, we have two delays, right? This will also have some parasitic capacitance here. So the first delay element will be this capacitor, and then again we have a delay due to this capacitor, right? So these two delay elements in the circuit will cause a large delay in the circuit. It adds two poles, right? It adds two poles, and these two poles simply mean there are two delay elements in the circuit, and delay in the circuit simply is not good. It will add instability to the system. So that is why we added a compensation. We did some compensation here to make sure that this delay is not delay do not harm us. Okay, so we added this capacitor to make sure that the overall system is stable. We did some pole splitting and all, everything is fine. So you see that in a three stage op amp like this, the situation is even worse, right? I mean, now we have three possibility of a three pole system, isn't it? We have three poles in the path. We have three delay associated with this particular op amp, isn't it? From input here to output we have three delay, and this is again not desired. So what do? We again do the same thing. We add Miller compensation everywhere. We put a Miller compensation here also. So this is called a nested Miller compensation. Okay, so this is nested Miller compensation. So focus on the words. I mean, why did we call it a nested? What do you mean by nested? So you see, this Miller compensation here is nested inside this Miller compensation here, and we if we add more and more stages, this will keep happening. Okay, so that is why it is called nested Miller compensation. Fine. So and what about the design constraint when we do this nested Miller compensation? So what was the intuition given to you? What did you understand? How do we decide upon the pole location and UGB of the individual transconductors here? Let's say this is GM1, this is GM2, and this is GM3. So what about what should we do here?
GM1 by CC should be greater than GM2 by CC2 should be
Okay,
greater than GM3 by CC3. CL maybe.
Right. So GM1 by CC has to be what?
Greater than.
No, it should be less than.
Less than
Yeah, it should be less than.
GM1 by CC less than
Yeah, less than
GM2.
it will be.
Should be less than GM3 by CL. And what was the, I mean, how did you come with this intuition? I mean, what was the reason behind doing this?
And the same to make the zero beyond omega unit.
Yeah, correct, correct. That is true. That is another insight. So basically, this will add zeros, and if we want to make sure zeros are outside of the UGP, we have to do this. But yeah, even easier way to understand this is the one that Professor Nagendra explained in the lecture, right? He said that basically we want to make sure that we have to make what do we want to accomplish by doing this finally, this Miller combination. We simply want to make an integrator, right? Our whole idea was to make sure that this behaves like an integrator, an ideal integrator, right? So this is GM1 and this is CC. All we want is to mimic this situation by doing all this, right? So doing this CC here, this CC here is added in negative feedback around this these two transconductors here. That is done in order to make sure that any current that comes here is simply going to pass through this and not going to pass through the parasitic that are present here. All the current that comes out of this GM1 has to go through CC. That is why we make sure that the CC is connected in negative feedback around this two-stage, whatever you want to say, in this two-stage op amp here. Now this two-stage op amp here, this has to behave like an op amp, right? It has to behave like an ideal op amp, correct? So and we know that any op amp behaves like an ideal op amp till what frequencies?
Unity gain
Till,
frequency.
till its unity gain frequency, right? So that is why the unity gain frequency of the innermost op amp, which is GM3 by CL here, this has to be the highest because this has to act like the required op amp till the maximum frequency, right? I mean this op amp will have to act like an op amp till the unity gain frequency of the of this op amp, right? So this has to be the highest. Now less than this has to be the unity gain frequency of this bigger op amp, right? And what is the unity gain frequency of this bigger op amp? It is simply GM2 by CC2, right? And this has to be ultimately bigger than the unity gain frequency of the subsequently larger op amp. Okay, fine. So that is clear. Now let's talk quickly about what is feed forward compensation. So this is clear, right, for everyone?
Yes, sir.
Okay. So let me clean it up. So now let's talk about feed forward compensation. That is another neat way to deal with things. Fine. Okay. So what do you understand by feed forward compensation?
Instead of making difference between input voltage, we provide direct current to the R that is just next to the op amp.
Yeah, correct. So let's say this was the condition. Fine. Let's say this was your buffer. Fine. And this is your okay. So what do? We since this DC gain is finite, right? And because of this G01, what happens? Or the current that is being pumped out of it is being some part of it is being stolen by this G01, right? And we do not want that to happen, correct?
Yes, sir.
So we want this current G01, G01 current, the current that is being taken by G01 should not be coming from this GM1, right? I mean GM1, whatever current is it is pushing should go directly into this capacitor. It should not be taken by this G01, isn't it? Fine. So what do we do to do that? We simply take these two from here, take this GM again, use two stage again here, and connect it like this, right? Is that clear?
Yes, sir.
Yes.
Fine. So and what was the, what about the speed of operation? I mean, what were the uh, so in between these two paths, this is one path, right, and this is another path. So let me make it clean so that you're able to understand. Fine. So this is the output. Yeah. And what did we want? We wanted to make sure that the current that is being taken by this should completely come from where? Should completely come from these two op amps, right? These two transconductors, correct? And when should that happen? At steady state, right? So you remember, I mean, this at steady state, the effect of this capacitor will not be present. I mean, this capacitor will not be effective, right? Steady state, saying steady state means what? This capacitor is effectively open, right? So all the current that it is pushing here is going inside GO2. So that should not happen at steady state. At steady state, the current that is required by this GO2 should be coming from this transconductor here. Okay. So that is why, let's say this is GM1, GM2, just say GMF. Okay. So that is why we make sure that these two transconductors, they are much slower. They operate much slowly compared to this transconductor. Okay. This transconductor should already reach its steady state by the time this should start acting. Okay. Before this should start acting, this transconductor should already reach its steady state. Okay. And when that steady state is reached, at that time these two terminals here, they are being sensed by this other op amp here, and then a resulting current is being pushed out of the second transconductor here to G02 to make sure that these two terminals here, they become equal. Is that understood?
Yes, sir. Why the upper path is slower?
Yeah.
I mean,
Okay. So fine, fine. So what I'm saying is that, you see, what is the what is the problem if there is a G02 here? If the upper path is not present, let's say, what is the problem if we have G02?
so some current will be taken from GMF.
Correct. It will take some, steal some current from GMF. And what is the problem if it steals some current from GMF? Ultimately we have to put it inside in some negative feedback. This GMF and this C, right? It should act as a integrator, isn't it? That is the whole reason. It should, we have to make an integrator here, right? But because of this resistance here, G naught, some part of the current is being stolen by G naught, right? And that is not desirable, because now this is not an integrator, it is a damp integrator. There is some damping in the integrator. It is not an ideal integrator. Okay. Other way to see this is that, when this integrator, an ideal integrator, has infinite DC gain, isn't it? What is the Laplace domain equation of an integrator? It is some omega u upon s, right?
Yes, sir.
Correct. Now what is the DC gain of this omega u over s?
Infinity.
Correct. It is infinity. So at DC, infinity. Correct. Magnitude of this is infinity. But because of this g not here, now the DC gain will drop, isn't it? It will be some k up, or let's say some, or make it, let's make it g upon g naught plus sc, right? And now at DC, that the gain is what? Gm by g naught. It is not infinity now, isn't it?
Yes, sir.
Correct. Now because if this gain is not infinity, if you put it inside in a negative feedback, if you put this integrator, this damped integrator in negative feedback around something, let's say this is a buffer. Okay, let's put it like this. If you put it in negative feedback like this, what will happen? Since the gain is not infinity, there will be some residual error, right? In between these two terminals. These two terminals should ideally, if this is Vref, then this should also be Vref, right? Ideally, if the DC gain is infinity.
Yes, sir.
But since these two terminals, the DC gain is not infinity, what will happen? This will be, there will be some error, right? In between, yeah, so there will be some error, V error, right? In between these two terminals, isn't it?
Yes, sir. I understood that.
Yeah, fine. So I'm
But
coming to the point. I'm coming to that point. Yes.
okay.
So yeah. So now this the same thing will happen here also. If you simply put this GMF and G02, right? Now that error is not desired, right? Now this error is something. The error between these two terminals is something which we have to take care of, right? So what we can do is, once this has already reached its steady state, okay, the stuff that is this basically this op amp here, once it has reached its steady state, that means it has already done everything, all the comparison, and there is some finite error here. Okay, let's say there is some error here. Okay, after that, what do I want? I want to make sure that this error is again reduced. And how will I do that? How will this error be reduced? If you do not know anything about the transconductor, you know that for a transconductor this equation has to be satisfied. GMF here times V error, okay, has to be equal to what? This current, right? G02 times whatever current is flowing inside. Whatever current is flowing inside this G02, isn't it?
Yes, sir.
Correct. So this current, if this current that is flowing inside GO2, it comes from somewhere else and not from this transconductor GMF, then this voltage will become zero, right?
Yes, sir.
Correct. Yeah. So that is what we are doing. We are providing another path here. This two op amps here, which are connected to this G02, which will operate only after the this thing, only after this second op amp, this one stage op amp has reached its steady state. Okay. So the the catch is that the second op amp here, it should reach its steady state when this upper op amp has to work. Now what do I mean? What do you understand by reaching steady state? Before it has one second. Yeah. Before this has to start working, this has to already stop. This should already finish its job, isn't it?
Yes, sir. Understood.
Yeah. So that is why this has to be fast. This has to be faster compared to this path here. Okay. That is what I meant. Fine. You understood, right?
Yes, sir. I understood.
Fine. So let's move on. Okay, so
A doubt.
yeah,
Hello.
yeah, yeah,
Sir, is how do we plan to make that the feedback loop be much faster?
yeah, yeah. So what do you mean by speed of a feedback loop? What is the measure of the speed of a feedback loop? How do you measure the speed of a feedback loop?
UGP.
Yes, correct, exactly.
You can
So if you want to make, so measure of the speed of a feedback loop is its unity gain bandwidth or UGB, right? So if you make sure that the UGB of one op amp is smaller compared to the UGB of of another op amp, then that means it is slower compared to another op amp. Okay,
understood.
and it is quite clear from here, right? You see that it is a two-stage op amp here, right? It is a two-stage op
It
amp.
will be slower. It will be
Yeah,
slower.
it will be slower by default, right? There is two parasitic poles here, so it will be slower by default. So I wanted to give another intuition here, so behind this. So what Professor Nagendra explained in his lecture, so that is fine. So I just wanted to give you another insight here. So what do we see here? So this is one op amp, right? Which we have studied so far, and we added Miller compensation here to make sure that it is compensated, isn't it? And what did this Miller compensation did? So if you have poles here, right? So let's say without this Miller compensation, your pole location was something like this. This is P1, and after, so let's say without Miller compensation, you had the following situation. We have P1, P2, and then we have UGB here. Okay. Clearly here the slope is what? Minus 40 dB per decade. Correct? Without any compensation. But what Miller compensation did is that it made the following thing to happen. This is now P1 prime with Miller compensation, and after this here it will start dropping here. Okay, and this P2 here, this P1 was shifted back, right? And the P2 location, it was moved further apart here. So let's say this is P2 prime, and after this it became 40 dB per decade, and here it is still minus 20 dB per decade, isn't it? So now this is the omega u here, omega u loop, and around this UGB the system is still having this minus 20 dB per decade slope, isn't it? Sorry. Oh shit. Fine. So the system is still having this minus 20 dB per decade slope, right? So that is why the system is stable, right? This is with Miller compensation. Fine. So now what this so this is another this is one method to make sure that the system is stable. So what is another way to make sure the system is stable? We just learned about it, right? That is feed forward compensation. So let's quickly look at that. uh, yeah, so let's say we do not want to do this. So what do? We know that the pole location here, the pole location here is what? somewhat like this. We have one pole here, P1, and then we have another pole here, P2, and then we have this 40 dB per decade slope here, right? This is without any compensation at place. This is P1 and this is P2. So we have these two pole locations here. This is minus 20 dB per decade, and this is minus 40 dB per decade, and this is the UGB omega u. But at this point the system phase margin, phase response, phase delay has already reached what, minus 180 degree, right? Close to minus 180 degree. So the system will be very close to instability. So one way to deal with this is that, let's say we follow the same graph here, the same slope here like this, but just before UGB I added a 0. Okay, what will this 0 do? It will simply do this, right? And this 0 should be what? It should be RHP 0 or LHP 0.
We lift up plane 0.
Correct.
LHP
It will be
0.
LHP 0, right? It should not be RHP 0. RHP 0 is more dangerous, right? So LHP 0 will be something which will make sure that the slope will be restored to minus 20 dB per decade, and the phase will be what? It will go down like this, and then it will again come up, right, to minus 90 degrees, isn't it? So that is why this 0 here. If this 0 is introduced at the right place, then we can make sure that the system is still stable, right? And that is what exactly is being done by this feed forward path, right? This feed forward path here, yeah, so this is, by the way, also called as feed forward path. The second path that I added in red, that is also called feed forward path. Fine. So yeah, so this is the feed forward path, and we name it by GMFF. So this feed forward path here, it will add up, it will result in a 0, which will make the system stable. Now I already told that this feed forward path has to be faster compared to this path, right? That was clear. That took a lot of time for me to explain, so I think everyone is clear on that this feed forward path here is faster. This is faster compared to this path, right? This is slower. Now
Yes, sir.
what do you mean by that? So one way to understand is that, you see, this slow path here is simply acting at DC, at very low frequencies. Okay, so at very low frequencies, at this point, around this point, or let's say even after that, the slow path gain is much larger. Okay, the slow path gain is much larger, but it is slower. But at very low frequencies, slow and fast we cannot differentiate, right? I mean, how can you differentiate between slow and fast? Will you be able to differentiate between one path is slow and one path is fast? When you apply when you apply high frequency signals, right? For a DC, there is no meaning of slow or fast. At every point in time, it is the same, right? You can never change. The DC level is never changing, so you cannot say whether it is delayed or not. It will always be the same, isn't it? So the slow and fast comparison can only be done when you have a reference frequency, right? And that frequency should be high enough to make that distinction, right? So that is why this fast and slow path distinction comes only at high frequencies. At very low frequencies, the slow path is the one which dominates because it has very high DC gain. It has very high gain, right? So every signal that is going to pass through it will come out amplified by a very large factor. Okay, and the same signal will also come out of GMFF, this path, fast path, but the amplification factor will not be so large. So are you understanding what I'm saying? Everyone, is everyone clear on what I'm saying?
Yes, sir.
Yeah, fine. So yeah, so this is basically, let's say let's say fast path. Okay, not this color. Let's use a different color. let's say this is the fast path. Okay, so this is the fast path and this is the slow path. So basically you can clearly see that the gain, this is basically the gain, mod of loop gain. Okay, so this is clearly much larger for what, for the slow path compared to the fast path. So the signal that is going to come from the fast path will not be amplified so much compared to the signal that is going to pass through the slow path. So that is why at very low frequencies the slow path is the one which dominates and the fast path is not in the picture at all. Okay, so at very low frequencies the overall loop gain is dominated. This overall loop gain, which is given in red, is dominated by the slow path. Okay, and the distinction is happening only at very high frequencies, where this you see that this black curve, which is the gain of slow path, becomes lower compared to this magenta curve. Okay, which is higher. So at very high frequencies this magenta curve takes over, right? And at that frequency the fast path becomes active. This is the frequency at which your signal, which is going to come through slow path, will be so attenuated that will not be able to compete with the fast path signal. The fast path signal is going to be amplified by a larger factor compared to the slow path at very high frequencies. Okay, so this is one way to understand this feed forward compensation. So anywhere if you find you have to stabilize a circuit, you have two options: either you use mirror compensation or you can use feed forward compensation. Both have their own pros and cons. Okay, fine. So this took a lot of time today. Let's quickly look at one question. Fine. So by the way, no doubt, right, in the explanations, in the discussion.
No, sir. Yes.
Fine. So now let's solve some questions. So this is an negative feedback op amp, right? Two-stage Miller compensated op amp, where you also have this resistor. And why? What is the purpose of this resistor?
To avoid zero.
Correct. It's a zero cancelling resistor, right?
Yes.
Now, first question: to which terminal A or B will you connect V naught for negative feedback? I mean, this is, let's say, A, and this is, let's say, B. So which terminal should you connect?
It's B only.
Okay, so my bad, this was already given. Fine, this was already written. Fine, let it be. Okay, so second question, this was not useful. Let's kind of remove it. Yeah, second question: find the DC gain omega U loop P1, P2 and RZ. What is the phase margin? So tell me the expressions of the DC gain omega U loop P1, P2 and RZ. So what is the DC gain?
GM1, GM2 by GO1, GO2. GO2 was not there. So GM1, GM2 by GO.
DC gain is what? GM1,
GM2 by GO.
GM2 by
GO1.
GO1. What else?
No GO2 was there.
Yeah, so what will be the this thing, DC gain of this op amp?
That will be
GO2.
infinity actually.
Correct. So DC gain is what?
Infinity.
Fine. Now tell me what is the omega U loop? How will you calculate? Yeah, Sagar, what was your question? If RL is present, should we go add to GO2? No, where is RL present, or where is GO2 in this question? Okay, so if RL is present, and so basically it should be You have to see whether it can be taken inside that or not. Basically, let's say if some go2 is present here, let's say some go2 is present here, and let's say some rl is also present here. So clearly here these two are in parallel, right? So you can simply add them. But um, let's say the situation is like this, that the rl is something like this. This is r2, this is r1, okay, and basically this is something like this. In that case you cannot simply add them, okay. You have to see how to add them. I mean, you have to break the loop and then you can see whether it is coming in parallel or not. But yeah, you can add. Basically you have to find the loop gain, okay, and in that loop gain you have to see how whether things are coming in parallel or not. Is that fine? Is this fine, by the way, the explanation?
So do we need to break the loop and then calculate?
Yeah, definitely you have to break the loop
So
everywhere.
if it is, yes, if it is just like non-inverting amplifier or voltage divider, then how do we calculate the load resistance of by breaking it?
Okay, let's take an example of what
Non.
non-inverting amplifier. So this is a non-inverting amplifier, right? This is a non-inverting amplifier, right?
Yes.
Now tell me, how do you find the loop gain? I mean, where will you break the loop?
After before minus
Yeah, fine.
terminal.
You break the loop here. You also short it, right? You also desensitize the input. Correct? Now we have to apply an input here, V test, and you have to find what is the V return here, right? Fine.
Yes.
But in that case, now at the output of this, let's say this was op amp. This is an op amp, okay? We will have something. You will have some parasitic go2, g0, everything inside it also, right? But outside it, we also have these two resistors, right? So these two
Yes.
resistors appear at the output, and they are in series, isn't it? So you also have to
Yes.
find. You will also have to consider its contribution. Is that clear?
Sir, actually,
You see, this will
we-
be something like this. So this is, let's say, your op amp here, okay, and let's say this is your op amp, and let's say it has some parasitic G0 to here already. There is some parasitic CL here, okay, and then again after that, what do we have? We have this. This is plus, this is minus, so this is grounded. Okay, from the minus side you apply it in a test signal here, V test, and here we have this R1 and then again R2, isn't it? And
yes.
right here we have this V return.
Yes,
Okay,
sir.
so you see that with in parallel to GO2 we also have R1 plus R2, isn't it?
Yes.
So here we have to consider R1 plus R2 parallel GO2. This will be the effective this parasitic resistance at this point.
So when we are going to calculate in like in this situation, non-inverting situation, we
Hmm.
have to break it. We have to break it just like when we are finding loop gain. Then we have to calculate it, right?
I mean, yes, everything that you have to find. I mean, DC gain, omega U loop, everything is for loop gain, right? So you have to break the loop and you have to find the loop gain. Then you can only comment on the
Even for resistance like this
what.
resistance. Even for finding output resistance also we have to break it, right?
No, 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 no. Okay, output resistance. Output resistance, I think I already talked about it, right? Let's say you have to find the output resistance here, right? So this is a closed loop system. There is nothing broken in this system, right? The question that is
Yes.
showing here. This is a closed loop system. You do not
Yes.
have to break the loop here. If someone asks you what is the in output resistance in the closed loop system, then you have to simply apply a test voltage here, right? You simply have to
Okay.
apply test voltage here, and then you have to find out what is the current coming out of it. Okay,
Okay.
and that for that you do not need to break the loop. You have to break the loop only for only when it is necessary. That means when you have to calculate omega u loop or the things which are required. I mean the things which correspond to a loop gain. Only those for those things. Only for calculating those things, you have to break the loop. Otherwise, you do not need to break the loop. Okay,
Okay.
fine.
So if input voltage is not given, so how do we calculate the current and get the output load? The, in the case of non-inverting terminal.
No, no. You see, for finding output resistance, I spoke it. I think it's. I talked about it in the last class. Maybe you should look at it once again. The last week's
Okay.
recording, you should take a look at it. I talked about it. Okay, fine. So if there is a doubt after that, you can ask me. Fine. So yeah, how do you find omega u loop here in this question? What do you do? Yeah. So now it should be not. It should not be much burden, right? Tell me quickly what is the
It,
omega u
it,
loop here?
Break a loop.
it will be GM2 by CC because the first pole will be at origin. P1 will be at origin.
What? Can you tell me again?
It is infinite DC gain, right? Means a
Yeah.
pole is at zero. First pole is at zero,
Hmm.
it is zero frequency.
Hmm.
So the second stage transfer function comes with like a pole one, pole of
Let's say
means
okay. So let's not do that. Actually, that will make the system unstable. So let's assume some resistance here. Okay, that is not good. That will make the system unstable. Let's assume some resistance GL here. Okay. So DC gain. Now tell me what is the DC gain? DC loop gain.
GM1 GM2 by GO1 GUL.
Correct. Fine.
Yes.
Yeah. Now tell me what is omega u loop?
GM1
Yeah. Go on. You are muted.
it will be GM1 by CC.
GM1 by
CC.
CC. This is the approximate location, right? So
Yes.
whenever you are told to find out what is the omega u loop, you should always I mean you should also check whether the approximation is holding true or not. By the way, approximation here cannot hold true, right? I mean there is only a factor of 5 here between CC and C1. So a better result would be what? To make sure that you write GM1 divided by CC times GM2 divided by G0 GL. Oh, omega u loop, right? So omega u loop is. Oh, okay. So omega u loop is fine. I was thinking about first pole. Fine, omega loop is fine. It is GM1 by CC, yes. Tell me now what is the pole location P1? What is
It
the
will
pole?
be GO1 by
Yeah,
C1 plus
C1 plus.
uh, this capacitance is there. Can you
Yeah,
CC
yeah,
into
right.
yeah. Okay. This resistance, Miller resistance is going to be RC.
Yeah, this will also. This is
C.
RZ, yes. So,
Give me a minute.
Oh, 1 plus GM GM to 2 by GO2. I mean, sorry. Yes, GM2 by GO2. Yes.
yeah. So, it turns out even after the addition of this RZ, the pole location do not change much, okay? Neither the pole location nor the omega u loop changes much, okay? Even after addition of RZ. Now, this is under the approximation that RZ is not very large. So exact expression for poles are
Af-
extremely,
af-
I mean, extremely cumbersome to calculate. So I have calculated it.
After adding resistance, it is no longer going to be a second order system, right?
Yeah, definitely yes. It is not a second order system. It is a third order system. But the
Uh,
third pole is going to be coming at very large frequencies outside omega u loop. Okay, so
And how come first pole is equal to G1 by C1 plus? Without resistance, that was fine, but
so
here
I will
Miller resistance is going.
correct. So have you done this calculation? I mean, it was told by Professor Nagendra to calculate, right? So did you do that calculation? For did you write
No,
the whole loop and then again calculate its P1, P2, P3?
no.
Okay, fine. So I did that. So I will. This is not here. Right. Yeah. So is this visible?
It's visible, visible.
Yeah, fine. So this is the system, right? This is the condition here. This is the system, and you see the when you make sure that RZ is equal to 1 over GM2, then you do not get any zero. Okay, and the denominator, it came out to be this one. This is the denominator. Okay, you see, this looks very beautiful, isn't it? So this is the denominator, and for it we have again 3 poles, and this 3 poles cannot be calculated like that. Okay, you have to give it to MATLAB and MATLAB will calculate. But if you make some approximations that again that the pole locations are I mean they are far away from each other, you have to assume this that where is that? Yeah, you have to assume this that all the poles are very far apart, that P3 is much greater than P2 and that is much greater than P1. That you have to assume. When you do that assumption, then you start getting these pole locations. You see, pole P3, it is like this. See, this is this was also explained in the lecture, right? That one pole is due to the resistor RZ. So you can clearly see that this is the pole here, RZ, and the three capacitors in series. You see here, you have this RZ here, and you have 3 capacitors CC, C1 and CL in series, and because of these 3 capacitors and RZ, you get a pole P3 approximately. And there are some other terms also, but let's say that they will not be much, they will not contribute much. This will be the dominating one. Okay, fine.
Is there any intuitive way to do this?
Yeah, so
Means
that the
to
intuition was
calculate,
already given in the lectures, right?
but
That is
with
the intuition, right? You have to assume, you can assume that because of this RZ, you will have a pole, and where will be that pole? You can see that RZ in series with 3 capacitors, isn't it? CC, CL, and C1.
can you say why first pole is not getting much affected by RC?
Okay, so let's assume that your system was very well designed earlier, okay, and the zero was very far apart, okay. Without resistor RZ, let's say that the zero was there, but it was at a very high frequency, okay. So that means what? Your system was designed properly, isn't it?
Yes.
Right. Now, but let's say you are not satisfied with that. You want to cancel this zero, okay.
Yeah, with the zero that was fine. How pole is not
No,
getting
no,
affected with?
that is what I'm coming to. That is what I'm
Uh,
coming to. Okay. Now
yeah.
let's say that your zero is not, you are not satisfied with the zero and you want to cancel that zero, right? So you
Okay.
will want to add this resistor RZ, isn't it? This RZ will be what? 1 over GM2, correct?
Yeah.
Now this 1 over GM2, if your amplifier was designed properly to start with, then basically this GM2 will be very large, isn't it? As someone also pointed out earlier, that GM2 has to be very large. If we make GM2 infinitely large in the limit, then basically the zero that it will introduce will be at very high frequencies, right? Now what was the zero location? GM2 by CC, right? This was the zero location. If we make GM2 to be infinitely large, then this 0 will appear at infinity, right?
Yes.
But let's say this 0 was not at infinity but at some finite frequency, but still, let's say GM2 was very large, okay? Then again, the 0 will be at a very large frequency, right? Is that clear? Fine. Now this RZ that will be 1 over gm2. If gm2 is very large, rz will be very small, right?
Yes, yes,
Yeah.
okay. Yeah.
Now rz will be very small. Now
Okay.
how can you understand it is that if rz is already very small, okay, rz is already very small, then basically the effect that it will have in the circuit will be very minimal, right? I mean, in the limit you can make rz to be so small that it is short circuited, right? Is that understood?
Yeah, okay.
So if in the limit you can make sure that rz is so small that it is short circuited, and if it is short
Yeah.
circuited, then you get the earlier circuit, right? Then
Yeah,
basically the
okay.
pole location was the earlier one. So what I'm saying is,
Okay.
if rz is very small, then the pole location will be changing slightly, but it will not change so much, isn't it?
Okay.
Is that clear?
And okay, and here the thing is like we should make RZ as small as possible so that the effect of RZ
Yeah,
will
I
be
mean,
very less.
RZ is not necessarily as small as possible. I mean, this was to just make our life easier. To
Yeah,
when,
means the it will be less than impedance of a capacitive impedance, means whatever the frequency of the circuit we are operating, it should be much less than capacitive impedance so that the effect will be reduced on the first pole.
I didn't get your point. What did you say?
So it the RC and CC are both are in the series, right?
Yeah.
So we should make ensure that RZ should be less than the capacitive impedance so that effect on first
Yeah,
pole due
correct,
to
correct, correct. I
RZ
mean,
is less.
yeah, you can say like that. In the frequency of interest, if the impedance provided by RZ is much less compared to the impedance provided by CC, then you can make that approximation. Yes, true. That is true. Yes. So I mean, that was the whole motivation behind doing that. So these are the approximate pole locations. So you can see P3 is because of this RZ, okay, and this will be at very high frequencies. Now the pole location P2 was actually what? This is a complicated looking expression here, pole P2, okay, but you can see that it also has the same kind of this thing. It also has the same kind of behavior. You see, there is this gm2 times cc divided by c1 expression here, and here also you have this cl into cc by c1. These two will be dominant here, okay, because all the other terms, if you check, you will see that for a very good designed op amp, all the other terms will be very small compared to these two terms, okay. And when only these two terms stand out, you can see that cc by c1 cancel, and you will get p2 is equal to gm2 by cl here also. So pole p2 is also fine. Now pole p1 is it comes out to be what? This is the expression of pole p1. So as he pointed out, as someone asked me, definitely because of this rz, pole p1 location will change, okay, but it will not change much, because if you have rz to be very small, this will not be very large, and effectively what will happen is you have this go1 divided by this gm2 times cc. This is the gm2 divided by go2 times cc. This was the Miller amplified term, right? So this will dominate here. Okay, so I will share this calculation with you all, but I will advise you to do this calculation yourself also. Yeah, someone has raised the hand.
Sir, P1 will be affected by that feedback factor, sir. If instead of unity feedback, if I connect the R feedback, then the P1 open loop systems will be affected, sir.
Now why? It should not be affected. Pole p1 p2 will not be affected, only omega u loop will be affected.
Only omega U loop will be affected.
Yes.
Okay. Thank you, sir.
Yeah. So
Hello, sister.
yeah.
So in the expression of PO1, so RZ is also in the feedback, so it should be multiplied by the Miller factor, right? But in the expression, it is not multiplied that the factor.
I didn't get your point. Oh, okay. So you're saying RZ should also be multiplied by the. I mean, it should be divided by the Miller factor. You are saying.
Yes, it's divided.
Yeah.
Okay,
So
so that means understood,
yeah,
understood.
fine, cool. So let's move forward. I will share this calculation with you. You should also do this calculation yourself once to get an idea. Okay. So fine. So we get this pole location P1. It will approximately be same. Again P2 will again be same, right? P2 is, what is P2 here?
GM2 by CL. You said approximate.
Yeah, correct. Yeah, this is all approximation. Yeah, so that guy who asked me whether adding resistor will change something or not. Yeah, so adding resistor may change the pole P2 location, okay? If the resistors are comparable to this parasitic GL, and if it is very small, then it will affect the overall impedance at this node, pole P2, okay? But it generally doesn't happen like that. I mean, that will be a poor design where this resistors at the output or the feedback resistors start to affect the op amp performance. That will be a poorly designed op amp.
Adding resistors will affect only the feedback factor, right? It is going to
No, no,
affect the
it will also
output.
affect the. You see the, if you have a resistor here. 1 second. Let's put another color. If you have a resistor like this, okay. Now this is a feedback, right? This is a, there is a factor of 2 here, right? Now this resistor here, it will definitely change the pole location, isn't it? Approximately it is GM2 by CL P2, but that is under the approximation that GL is much lesser than GM2, right? And whatever else, I mean whatever is connected here, that is much less compared to GM2. That is the approximation here, right? But if this GM2 becomes comparable to 1 over R, then you cannot make that approximation. So that is why it will affect, but it will affect only slightly. I mean that is, I mean the a good designed op amp will make sure that this R is not so small that it will start to affect the operation here. Is that understood?
Yeah.
Yeah.
Then the resistance, output resistance will be GL plus the resistance which is connected
Yeah,
there, right?
definitely yes.
Yes, yes. Okay,
GL
fine, fine.
plus whatever is there. I mean this is the approximation P2.
Yeah.
Correct. Fine. So yeah.
So one doubt.
Yeah.
If we have some output load capacitance, won't that change the position of P2?
Yeah, definitely it will change the position of P2.
So for the questions, we have to consider the output capacitance and the output resistance, if there is, and the feedback loop, whatever
Yeah.
be the gain for which the feedback loop is designed for.
Yes. 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 And always remember that in the answers you will always have a range. I mean, the answers are not like it should be correct to 2 decimal places. I mean, you have to, they will always provide some tolerance, okay, in the assignments. There is some tolerance, like the expected answer, the correct answer is expected to lie somewhere between two limits, okay. So if your answer lies in that limit, then you will get the correct answer. You will get the correct marks for that. Fine. So yeah. Yeah, so what is RZ here? If you want to cancel the 0, what should the RZ be here?
GM2.
Correct. Fine. Now modify the architecture to obtain a closed loop gain of 2 using resistor divider and the feedback loop. So how will you modify this architecture to get a closed loop gain of 2?
Resistor divider of R and R. Means we can place between output and the peak.
Yeah. So the one that I've been showing so many times, right? Like this. This is R. This is R. Correct. Right. So
Yes, sir.
yeah. Now you see, when this statement is made that you have to add resistors here, the another statement is made here that assume that the resistors do not change the operating point of GM2 and the conductance of GM2 is much larger than the additional conductances. So this is what I have been emphasizing so far, that when you add these resistors, it should not should not be affected, it should not affect the existing op amp so much, okay. It will add some conductance at the output, but that conductance should be much smaller compared to what already is present at the node, okay. Only then can you make only then can you say that your op amp is designed properly. Yeah, Venkata. Yes.
If there is a buffer between the out means the capacitance and the V out,
uh,
then there will be no effect of
correct,
this
correct,
resistance,
correct.
right?
If there is a buffer
Resistance.
here, like
Yeah.
this, sorry, this is a inverter. Yeah, if you have buffer here, then you have no problem. Yes, because a buffer is an ideal buffer is what it can provide infinite amount of current. I mean, it has zero output resistance, so it has no problem. But if there is no
Sir,
buffer,
sir,
yeah.
please explain the effect of these resistors on GL, sir. Output conductance.
So I
Please.
told na. I mean, this is what I've been saying so far, so many times now. You see, when you break the loop and you find out what is the effective conductance at this node, right? So what is the effective conductance at this node, other than this part? So what is coming parallel to GL? Tell me.
So it is R1 in series with R1.
This is R, not R1. Okay, so yeah, fine. So
Yes.
this is 2R, right? So R plus R is 2R, and that is in parallel with GL, right?
Oh, okay, sir.
So the effective conductance at this node will be what? GL parallel to R, right?
Okay, okay, sir.
Yeah, fine. Okay. Now tell me, under this condition, sketch the magnitude of the loop gain with respect to frequency. So tell me what happens to the loop gain here when you do this. When you put I mean, earlier what was the loop gain? Uh, this is
Reduced by
DC gain
20.
or normal gain?
so earlier the loop gain would be like this, right? First there is P1 here, then there is, let's say, omega u loop here, and there is, then there is P2 here. Yeah, so this is the earlier case, right? When there is no these registers are not connected, that is the case. Okay, but after the connection of register, what should happen? The loop gain should,
Deep DC gain decreases by half.
yes, yes,
Omega U loop decreases by half.
correct. So DC gain
And T.
decreases by half, omega u loop also goes down by 2 times, but the pole
Yeah.
location do not change, right? I mean, that is the whole approximation. And then this start to dip now, right? Now can you comment
Yes, sir.
about the phase margin in this case? I mean, this is the case without resistive feedback,
Phase
and
margin will be improved.
with resistive feedback, right? So tell me what was I mean, and this, if this is the gain earlier, then this should be what? This should be 6 dB below, right?
Yeah.
So this is loop gain in dB, right? So this is 6 dB below, and this omega u loop here will be what? By 2, isn't it? Fine.
Phase plot is not going to change.
Phase
Uh,
plot is not going to change, yes.
yes, so that initially at omega U loop there will be more negative frequency, means the phase offered by it.
So let's
But
plot the phase response. Why
okay.
don't we do that? Yes. Before that, let me do something. It's making me extremely uncomfortable. Yeah. So yeah. So this is let's say this is 0 degree. Okay. And let's say this is 45 degree. This is 90 degree. This is 135. And this is 180. Minus, 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 minus. So at pole P1, what will happen? This will go to minus 45 degree, right? And it will come to minus 90 degree at,
10 times P1.
correct. So at 10 times P1, this goes to 90, basically 90 degree, right? So this is omega u loop, which is the critical point. This is also omega u loop. Let's not use this color for this. This is omega u loop, right? Earlier one. So around omega u loop, this will start. So let's say P2 and omega u loop do not vary by do not differ by a factor of 10. It is less than 10. Then at omega u loop there will be some dip, right? There will be some dip, and at exactly P2 it will reach minus
Minus
135.
135.
Correct. Let's make it. And then again after 10 times larger this will go to minus 180, right? Fine. So this is the plot earlier. Now because of this DC gain will drop, so what will happen? The phase margin will be what? I mean the phase earlier was what? The phase margin earlier
Here
was what?
was phase phase margin increases actually because
Right, this
phase
was the
was
earlier phase margin, isn't it?
yeah.
Yeah, and this is the new phase margin. So the way I've drawn it, it doesn't look like much, but yeah, so you understand, right?
Yes, sir.
So phase margin did change, and phase margin did change here. Phase margin increased. So this is why uh, Professor Nagendra also emphasized in his lecture that for a Miller compensated op amp, which is the case here, right? This is a Miller compensated op amp. For it, the worst case happens worst case is the worst case is when you design it for unity gain configuration. Okay, that is when it has the highest chances of going outside of stability, of becoming unstable, right? You also see that when it was unity gain feedback, the phase margin was comparatively lower, right? Isn't it? But when you design when you increased its gain, okay, when the gain was higher, at that time the phase margin improved, right? When the closed loop gain increases, the phase margin in this case also increases. Okay, so that is why when you design this op amp, Miller compensated op amp, when you try to design it in industry, okay, when you want to do something practical or useful with this op amps, then you have to always make sure that it doesn't become unstable, right? And let's say you want to make a product out of op amp. Let's say you want to make a op amp and you want to sell it everywhere in the market. Now you do not know what the consumer will be using it for, right? They can use it for unity gain configuration, or they can also use it for high gain application, right? So for you it will be a difficult task to make it stable across all possible cases, right? So what an engineer does is that he or she has to design it for the worst possible scenario. I mean, for the worst possible case where his or her op amp can become unstable. Okay, and what is the worst possible case here?
Unity gain.
K
Yeah,
equal to what?
correct. So the
Okay.
worst possible case is when when it is connected for when it is implemented for unity gain configuration. Okay, that is the configuration in which it has the highest chances of becoming unstable. So if your op amp is doing very well in the unity gain configuration, then it will do better in all the configurations. Okay, so that is what was required of this question. So that is what I wanted to say in this question. So is there any doubt in this question?
No, sir.
Yeah, so you see here I have not calculated anything because the calculations are pretty straightforward here. I mean, that is what you also have to do in all the assignments. The assignments are straightforward. You just have to put these equations, these expressions there, and you have to find out the required values. Okay, the point that I wanted to deliver today was the intuitions. Okay, so I guess everything that I talked about so far in today's tutorial, everyone followed that, right?
Yes, sir.
Yes, sir.
Yes.
Yes,
Fine,
sir.
Yes,
fine,
yes,
fine,
sir.
fine, fine.
Mm.
Very
Yes,
good,
sir.
very good, very good. So
Yes.
if that's okay, then let's meet in the again next Sunday. That's what I had to say today.
Sir, one question for
Yeah,
you.
yeah. Go ahead.
Sir, in assignment week 4, that first question, that overall gain of that op-amp, in
Huh?
that case, so should I add that load value with the GO2?
I didn't get your question.
In week 4 assignment, the the first question, what is the overall gain of this op amp?
Okay, in the DC for the DC gain part,
DC
they
Yeah,
gain.
have
yeah.
just taken GM1, GO1, GM2, GO2, sir. But GL was not added to the GO2, and the answer was skipped.
But the answer, I mean, they asked to
Yes,
find for the
In
op amp,
80
right?
dB, so it's not considered that RL.
No, but
I
this.
mean, sir, that should be considered, right?
Actually, they
Because it is.
ask
Yeah,
only for
that
the
considered. Okay,
open.
okay.
Yeah, yeah, it should be
Specifically
considered.
about the op amp.
Yeah, yeah, it should be considered, but actually the op if it is no, so if they ask strictly of the op amp, then it is another thing. But if it is
They
not asked
ask
like
for
that,
the open gain, overall open gain, not for the Unity loop configuration.
I know because I got the others wrong. All of the others wrong. That's why.
okay, okay. So you see, a lot of times these confusions can arise, but the thing is that you see, there is nothing. I mean, every if you have understood it, then it's not a problem. Sometimes these confusions arise, but the point to uh, the main point is that you understand that. Okay, if you understand, then it's okay. I mean, sometimes these confusions arise. It is just. I mean, you have to think from the point of view of the administration. Okay, so they have to manage it for the whole country. Like, so people across the country have to are going to take this program, and it becomes difficult and cumbersome for them also. So that is why these things happen. But yeah, so generally when people ask to find this DC gain, then basically they mean that DC gain has to be found out for the loop gain. Okay, for the loop gain you have to find the DC gain, and when you have to find the DC for the loop gain, then basically you also have to consider the load resistor and load capacitors also. Okay, but I mean, I have seen them framing question like this, that you have to consider that you have to find the DC gain. If they want you to consider the load resistance also, then they explicitly mention it there, that find DC gain with the load resistance, like that. Okay, so like this problem, uh, this is one question, right? So you see, in this question they clearly mention that determine the overall DC loop gain of circuit of figure 2. That is what they mentioned. They didn't say figure 1. They said figure 2. If they do that, then you have to consider RL and CL also, okay? If they do not, then basically you can ignore that. Is that clear?
Sir,
Yeah.
No, sir.
Yeah, yeah, yeah.
Sir, sir, if this is the case, the answer will be 60 dB, sir.
What is the answer to 60 dB? I have not
But
solved this
they have
question.
given 80.
I'm not solving this question also. I mean, I'm just saying, for an example.
Sir, even in assignment 5 also, there are ambiguities in questions 9 and 10 regarding CL.
Okay, so that is what I'm saying now. I mean, they are ambiguities. I do agree, but again, this is not my jurisdiction. If you have that problem, you have to you can mail them. Okay, you can mail your concern to the administration. They will look at it. This is not my.
And one more, sir,
Yeah,
one more doubt we have, sir,
yeah.
regarding the poles P1, P2, Z1. Is it necessary to specify the sign as regarding that one? Sign of that one. Location
No,
on
they.
the left hand.
I don't think they position of the terminal. I don't think they want to ask you that. I don't think.
Actually, in answers, they just considered magnitude.
Yeah, so yeah, so magnitude you can write, yes.
Okay, okay, sir.
Generally, people do not consider the location. I mean, it is understood that it is left half plane.
Okay, okay, sir.
Sir, I have one doubt.
Yeah, go ahead.
Sir, in the two-stage mirror compensated op amp, if
Uh-huh.
we want to calculate the overall transconductance,
Uh-huh.
then we have to open all the capacitors.
Yeah, actually, yes, that is how you have to do it. I mean, that was a very ambiguous question. It is not a right way to ask this question. So that is not a good question per se. Okay, you see, transconductance is basically overall transconductance is actually what. In this case, you can clearly see that the transconductance will be amplified, isn't it? You see that this transconductance here, GM2, is at DC at very low frequencies when these capacitors are not there. Then basically this transconductance GM2 will be amplified by the gain of this first block, right? Let's say this is GM1. Let's say this is GM1, this is GM1, and this is GDS1 or G01. So the overall transconductance will be what? GM2 times GM1 divided by GO1, right? This is the overall transconductance. So this is what they mean, but this is not a very right way or good way to ask question. I mean, this doesn't make much sense. But anyway, so you get the idea, right?
Yes, sir. I got it.
Yeah.
So, always when we consider
Hmm.
um, for example, if we think about the input impedance with the Miller capacitance,
Uh huh.
we've considered that as GM2 by GO2 plus 1, which is a DC gain, but it's not actually uh, frequency dependent, right? That's a DC gain multiplied into the
Yeah.
capacitance C.
Right.
So,
Right.
how is that? Is it? How is that correct? I mean, how is that's a DC term? That's just applicable for a singular frequency, not for all
Yeah.
frequencies, right?
Yeah. Understand. So that is a very good question actually. So you see, this is an approximation. Like people say that. I mean, we have understood it in this way, right? That P1 is appearing because this capacitor is being multiplied by this, right? And you say that P1 appears here and then it starts with 22 per decade and then P2 is at a very high frequency. But the question is that the very right, this is a very right question, that this P1 is only at very low frequencies. This P1 approximation holds only for low frequencies, right? But at very high frequencies, this curve should not be like that, right? And P1's location is actually, we say that it is because of the amplification of this capacitor C by the Miller factor, right? That we say, but strictly
Yeah.
speaking, that is not the case. But the thing is that all these approximations hold as long as the this GM2, this second, this transconductor here, its unity gain frequency is, as long as it is larger than the unity gain frequency, all these approximations hold. This is not strictly true because that is not happening. It is indeed a frequency dependent gain, so that is not true. But as long as this gain, this block here, it acts like a this thing op amp, it is fine, and it acts like an op amp till its unity gain, right? So that is why it's okay. I mean, it's fine. But strictly speaking, it is not the case. That is not true.
So it's because P1 is actually very, very small and it's
Yeah.
very close to the zero frequency that this approximation holds good.
I mean, P1 is no, not actually not P1 location by itself, but P1 and P2. Okay, if the relative distance between them is too large, okay, and the unity gain frequency appears before P2. I mean, clearly here the unity gain frequency is here, right? And it is
Yeah.
before P2. Then this approximation is approximately. Then this is approximately fine. Okay.
I understand. Which means the integrative action works for frequencies up till omega u loop,
Yeah.
right?
Right. Yes.
Okay. Okay.
Mm. What you can
Thank
do
you.
is you can also do the following. I mean, as an exercise, what you can do, you put resistors here, GDS and C1 here. Okay. You also put GL and CL here, and what you can do is you can calculate what is the what you can do is you can calculate what is the, you give a test voltage here and see what is the current coming out. Okay, this current exact value calculate. Okay, not the approximate things that has been taught to you in the class. You find the exact current. This current will have some real term, and this current will be in terms of S, right? This will be in
Yeah.
terms of S, and so basically it has some real part and it has some imaginary part. So you split both of them into you see how the so basically when you do IT by VT, you will get the overall admittance, right, at this node. When you do IT by VT, you will get admittance at this node, right, at this
Yeah.
node. Similarly, you do the same thing here also. You give VT here and you measure what is the current coming out of it, and you find the admittance here also, and they will both have imaginary and real components. And what does imaginary component in admittance mean? It is basically due to the capacitor, right?
Yeah, capacitance. Yeah,
Correct.
because
So you
yeah.
see what is the value of that capacitance and what is the value of the real term. That will be basically corresponding to a conductance or a
Interesting.
resistor. Okay, and you find
Yeah.
out what is the pole location because of that. So you will get some interesting ideas or intuitions. Okay.
Okay.
This
Sir,
yeah.
sir, can you suggest a reference book in which we find such type of problems?
It's a problems. I mean, I have been telling you many times. I mean, this book by Professor Behzad Razavi is good. I mean, another book is again the same old Sergio Franco's book. Okay.
So in that, sir, in that these type of problems are not available, sir.
Okay, so you can maybe
Only circuit level problems are available.
so you want block level problems.
Yes, sir. Yes, sir.
No,
Yes, sir.
block level problems are in plenty in Professor in Sergio Franco's book.
No, sir. In that also I didn't find, sir.
No, no, I how what is that? I mean, I also follow that book. I think I have read everything from that, and I have seen a lot of block level problems there. That the title of the book is designed with operational amplifiers. The operational amplifier block is actually the block level representation of op amp is used there at several places. Okay, so
No,
it
sir.
is
I have the hard copy also with me, even at present. The second
it,
edition I
no, no,
have.
I also have the hard copy. Okay, I also have the hard copy, and there are a lot of problems there also.
Sir, can you suggest one page number such that I can see that one?
I can I'll have to look at it. Okay, so 1 second. Let's see. First chapter was circuit with resistive feedback. First chapter is nice. Second chapter is also fine. Uh, then there is first and second chapter have a lot of problems in that they do not have this circuit level device level problems. They have block level problems only in the first and second chapter.
But they are op amp based problems, sir, not
Yeah.
transconductance based problems.
So what is this big deal? I mean, if you want to put transconductors there instead of op amps and solve it. Okay, so other place we can where you can look at look problems like this is you can go to the website of ICS website of IT Madras. Okay, there
Okay.
they have a lot of ongoing this thing that all the courses they take in the class they also upload it for everyone.
Okay.
They also
Okay.
have the assignments there, so you can practice the assignments there.
Can we access, sir?
Yeah, you can access. It is open to everyone.
Okay. Okay, sir. Okay, sir.
Okay.
Which textbook, sir? Name?
The textbook is Sergio Franco. That is the textbook. Other textbook is by Professor Behzad Razavi. Okay, these are the two textbooks. You can also go through the ICS website. Okay, that has some. ICS website is basically the IC design website of IIT Madras. Okay, so there they all the courses that they take in this area. They also upload the lectures there also. Okay, and the assignments are also there uploaded there. You can look at this assignments there. But their I mean their difficulty level is slightly higher, so that's just there. Fine, so let's meet again next Sunday. Okay, thank you for joining today.
Thank you, sir. Thank you.
Okay,
Thank you, sir.
welcome.
Thank you, sir.
Yeah.
Thank you, sir.